Plasticity and functional recovery. Plasticity is the brain's tendency to change and adapt functionally and physically as a result of experience and new learning. During infancy, the brain experiences a rapid growth in synaptic connections, peaking at about 15,000 at the age 2 to 3 years. As we age, connections that are not in use are deleted and other more frequent used connections are strengthened, and this is called synaptic pruning. Neural connections can change or be formed at any time due to learning and experience. Functional recovery of the brain after trauma. Following physical injury or other forms of trauma, for example stroke, unaffected areas of the brain are often able to adapt and compensate for those areas that are damaged. The functional recovery that may occur in the brain after trauma is another example of neuroplasticity. The healthy brain areas may take over those areas that are damaged, destroyed, or even missing. Neuroscientists suggest that this process can occur quickly after trauma, spontaneous recovery, and then slow down after several weeks or months. At this point, the individual may require rehabilitative therapy to further their recovery. What happens in the brain during recovery? The brain is able to rewire and reorganize itself by forming new synaptic connections close to the area of damage. Secondary neural pathways that would not typically be used to carry out certain functions are activated to enable functioning to continue, often in the same way as before. This process is supported by a number of structural changes in the brain, including axonal sprouting, the growth of the new nerve endings which connects with other undamaged nerve cells to form new neural pathways, reformation of blood cells, and the recruitment of homologous similar areas. Homologous means similar areas on the opposite side of the brain to perform specific tasks. An example would be if Broca's area was damaged on the left side of the brain. The right side equivalent would carry out its functions. After a period of time, functionality may shift back to the left side. Support for plasticity. Maguire et al. Looked at London taxi drivers and found how there was more volume of grey matter in their posterior hippocampus than in a matched control group. This part of the brain is linked with the development of spatial and navigational skills. Taxi drivers take a knowledge test to recall streets and possible routes. This learning experience can alter the structure of the brain. This was also positively correlated with the length of time that they had worked as taxi drivers. The strength of this is that it shows support for the existence of neural connections, can change or be formed at any time due to learning or experience. Another strength is that it shows evidence for synaptic pruning as their knowledge strengthened over time. Support from animal studies. So Hubble and Weasel, they sewed one eye of the kittens shut and analysed the brain's responses. They found that the area of the visual cortex associated with the shut eye still continued to process information from the open eye. This study shows how loss of function leads to compensatory activity of the brain, and this is also evidence for plasticity. Another strength is that it supports the concept that the brain can rewire itself and has the ability to create secondary neural pathways. Evaluation. One strength of plasticity and recovery research is its practical application. Our understanding of processes involved in plasticity has contributed to the field of neurorehabilitation. Techniques such as movement therapy and electrical stimulation of the brain's counter deficits to cognitive functioning experienced following a stroke. This shows that although the brain may have the capacity to fix itself to a point, this process requires further intervention if it is to be successful. This increases the appropriateness of the research as it can be used in real life. One limitation of neuroplasticity is potential negative consequences. The brain's ability to rewire itself can have maladaptive behavioral consequences. For example, prolonged drug use can result in poorer cognitive functioning and increases the risk of dementia. Such evidence suggests that the state that the structural and physical processes involved in a functional recovery may not always be beneficial, thus decreasing the appropriateness. Supporting research for neuroplasticity comes from an animal study by Hubble and Weasel. They sewed one eye of a kitten's shut and analysed the brain's cortical response. The area of the visual cortex associated with the eye suit was not idle but continued to process information from the open eye. This pioneering study demonstrates how a loss of function leads to compensatory activity in the brain. This increases the validity of the idea of neuroplasticity as it provides evidence that it is possible. A further limitation is that the relationship between age and plasticity is complex. Functional plasticity tends to reduce with age. The brain has greater propensity for recognition in childhood as it constantly adapts to new experiences and learning. However, Bazzola et al. Demonstrated how 40 years of goal training produced changes in the neural representation of movement in participants aged 40 to 60. This shows that neuroplasticity does continue throughout our lifespan.